fact that this is completely about blockchain, not any cryptocurrency stuff, and this is completely on a technical note. It will be purely about code and stuff. There were some suggestions last time saying hey, we need to see code, we don't mind sitting and writing code. That was one. And the second part was, last time was much longer, we went until 1:30 almost. So we sort of said no, this time we'll make it much shorter and not make a much longer one. But there was pretty good participation around last time. I mean, if you guys missed it, you can go back to the Facebook page or I'll put a link. Because there is some amount of continuity compared to last time, which you guys are losing in some ways, because we did an introduction to blockchain and the whole thing and how hashing comes into the picture. And today we are primarily discussing hashing, right? Because last time there were a bunch of questions around, hey, how do I even, for example, if I'm creating a web application, how do I store the user's credentials? I mean, some people were surprised when I said you don't store the user's password, rather you store the hash of the password, right? In fact, I remember one guy coming and asking me as to, hey, can you do a demo on how you do that, right? So that's something that I have included this time around. So how many of you know about hashes? How many of you used hashes, hash algorithms, the science behind it? Okay. So here I'm not going to go through the mathematics and science of hashing because that will make us all go to sleep on this nice Saturday morning, which is pretty nice weather to stay in bed, have coffee and pagoda or something than sitting in a meeting room. So I'll not be going into the mathematics and science of hashing. I'll not be comparing the hash algorithm, saying what's good, what's not good and all that stuff. One of my assumptions is that you guys, if you use hashing, you know what's the difference between knowing the difference, you know what is SHA-1, what is SHA-256, when do you use PKFT, P2 algorithms, speed and all that stuff, right? So we'll just go through. Okay, so what's a hash function? I mean, other thing that we discussed last time is it's not just going to be one way when I'm talking and you guys are listening. It's more about all of us participating. So what's a hash function? I'll put it over there, but still, I'd like to hear from you guys. What's a hash? You can be loud, it's okay. There's no right or wrong answers here.
Hash is a code which is hard to read. Yeah.
Okay, perfect. So this is a hash that I just got out of somewhere. So yeah, it is pretty hard to read. I mean, there is nothing we can make sense out of that, right? What else? What does a hash denote?
It's unique.
Perfect. Okay, so like you were saying, sorry, I didn't get your name. Aman. Thanks for the thing, Aman. So a hash, as I said, is unique. One of the best part about a hash is that it's, in technical terms, it's called collision resistance. That's a hash should not collide with another hash. So a collision here is two hashes being the same, right? So one of the best parts about a hash is that it has to be collision resistant. So a hash denotes something of value. In a very shorter form, right? It could be a file, it could be any sort of digital entity. A hash function will take any digital entity and produce a representation of that digital entity in a much shorter form, right? And it will uniquely identify the digital entity. The digital entity can be MP3 file, it could be a JPEG file, it could be a text file, it could be a database record, and anything that is digitally represented, right? And not many of us know, but hashes rule our world on a day-to-day basis, right? The TCP stack uses hashes to sort of make sure that the messages being transferred across are validated. We all use net on a daily basis. We all use TCP on a daily basis. So it does that. Some of us use Git as a repository. So Git has a huge amount of hashes everywhere. Some of us use databases, Cassandra, Redis, a lot of other key value stores. They all use hashes in the background. So hashes in some ways form the backbone on a lot of systems that we have, and an understanding of how a hash works is pretty key, right? So a hash is generated by a one-way function. So what's a one-way function?
Cannot be decrypted.
Cannot be?
You cannot get the digital document which you use to create the hash from the hash.
Yeah, perfect. What else? Bangalore is known for its one-ways. Okay, so like you were saying, a hash, what you said is also correct, but this is not got anything to do with cryptography. Cryptography is still way off, right? This hash is completely different and cryptography is completely different. There are cryptographic hashes and hashing is used hugely in cryptography also, but hash still is independent of cryptography completely on its own, right? So a one-way function is you pass in something, you get an output, but you can't reverse it. For example, addition, the mathematical, commutative, associative, all those which allow you to turn things around and still get the same inputs that you have, right? But a one-way function, once you pass data in through it, and once the output is there, you cannot reverse it back. Yeah. Okay. Right? So there is no way you should be able to reverse it back and get the inputs for that particular function. Mathematically, there is a huge amount of mathematics behind this, so I'm really trying my best not to get into the mathematics of it, right? Minimal collision. So again, as we were saying initially, right, uniqueness is a key property of a hashing function. A hashing function should be designed in such a way that no two inputs will produce the same output, right? And the other beauty of the hashing function is that the key space is huge. You can input, let's assume you have 1 million pictures, you pass them through a hashing function, the probability of getting the same output is 0. For example, if you take SHA-256, there hasn't been any collision in SHA-256 and some of the other. Just give me a minute. So that's number 2. Number 3 is it should be easy to compute. I mean, there should not be a hash function can't be slow. It can never be slow. Because for example, if you take TCP checksumming, in a lot of them, it takes around in a minute or maybe in less than a second, there are around 600 to 700 operations that a TCP checksum performs. So something like a TCP checksum can never be slow, right? It should be hard to reverse engineer. Again, that's same way with the minimal collision that we talked about. There is no way you should be able to reverse engineer, because if you're able to reverse engineer a hash, then you're breaking the hash completely, right? So that's in a simple way. I mean, that's what a hash function is. Anything you guys want to add? Okay, I mean, so we're talking about where is a hash used? So a hash, I put in a bunch of things where a hash is used. So a hash is generally used as digital fingerprints because a hash generates a unique value out of the digital asset that you pass in. Let's assume it's passing an MP3 file. For example, if you take BitTorrent as a example of a torrenting framework, right? I mean, how many of us know how BitTorrent works? I mean, it's the same example we took last week. Can you tell us how BitTorrent works?
It works with peer-to-peer connection.
Okay, let's assume you take a music, let's say Napster. MP3.
Via peer-to-peers, for example, surrounded by like send the file to our.
And how do you send the file? And then
It's like a decentralized way, in a decentralized manner.
okay. Let's assume that 10 people have the same MP3 files.
Yes.
Or the same music files.
So over
and
the,
100
on,
people
the
want
data,
it.
on the database on a real-time basis, we can check how many people has got that file, and accordingly.
So how does it identify that file? How does it know that these 10 people have a file?
Via peer-to-peer application.
How does it identify it?
Compared
Yeah, I mean it transfers it peer to peer. You're right. I mean, so if there are 100 people and 10 of us have it, it takes those 10 copies and moves it across to people across, right? To all the 100 people on the network. But what does it do uniquely that the transfer is fast and a lot of people can share it, And even in networks where we are not always connected, even if the network breaks or something happens, it still is able to transfer files, right? Whereas if you're doing a regular file copy on a Windows or a Unix network, if you lose your network, that's it. You need to recopy the whole file again, right? So how does that work?
It hashes the file and checks that who all have the same file. If one connection breaks, then you search for the who has the exact same file, the network, and then ask it for that particular chunk.
Perfect. So what it basically does is, if you're loading a particular MP3, let's say you upload Despacito or something like that, it hashes the whole MP3 file and generates that unique string that we said initially. And let's assume 10 people have the same file. Now that MP3 has the same signature, right? So everybody on that network has a hash of that particular file. And it doesn't look at the name, it doesn't look at anything else to say you could have any file, you could have any MP3 and name it as Despacito, right? I mean, it can't uniquely identify. But the hash of that is what uniquely identifies that file. Then it knows there are 10 people who have the same digital asset on 10 different locations. And the other thing that it smartly does is, if it is a 2 MB file, it breaks it into much smaller chunks. It just doesn't take that whole file, hash it and send it across, right? So what it does, it breaks it into much smaller chunks and again hashes each of these chunks. Breaks it down into 50 chunks, right? And it hashes each of these chunks and it maintains a list saying who has which chunk in this. And that's the reason, if you notice it, there is a bar down which says who are the peers, who are seeding it, which pieces of it do you have, which pieces are strongly available on the network, because some people will have more pieces of that particular block, right? So it hashes each and every block over there, and then it starts moving these blocks, and it knows what is the whole addition of all that blocks, which results in the final hash. So it's always checksuming and figuring out. Maybe I could have one much more into that. So it's breaking it down, hashing every piece, and also maintains a complete hash of the whole file at any point in time. So it can always calculate which piece of the block do you have, and it also knows at what point in time you have the whole block, right? So that's one of the popular uses of a hash and checksum function, right? The other one that I can think of is a hash table. How many of you guys use a distributed key value store? Configuration files. So, can you tell me what's your DKT, what's your distributed key value store?
To be like in a project, we just use this hash table for storing our configuration properties. So what's the exact question?
So so yeah, perfect. You store your configuration as a key and value, right? There's a key value pair. So what's unique about a key value pair in a hash table? Why not just store it as an array or anything else? What's so unique about a hash table that you store it in a hash table?
Lookup is faster. Why? Because so since the size of the hash is limited, so the space is also limited to distribute it into various buckets, and then the search space will decrease for each particular hash.
So do you guys get that? Okay, so again, I'll just elaborate more so you can correct me if I'm going wrong. Okay. So what happens is, a distributed key, forget a distributed key value store, let's just come to pure key value store, right? A key value store stores a key and a value, and the way you find a value is you use a key, right? Again, we will run into search issues, right? There are login, go login, and login. You run into all this search complexities as to how do you find. For example, if you want to find a particular value, you need to find its key and then search through for that key. Correct me if I'm okay. You have to search through for that key, and that leads to a lot of issues in terms of search algorithms, right? But beauty of a hash table is that you hash the key, and the key has a bucket space within which you store it, right? And it's mapped, so I know at any point in time, if I hash this key, the value that I get is the location where it is exactly. So it's a direct, the time complexity in this case is completely reduced. So the time complexity in this case is completely reduced. There is, it leads to much faster searches. And if it's further in a distributed space, you're not just using the key value store in one location, but you're moving it across to multiple systems on the network, it's much more faster, because then your hashing is also telling you which particular system the particular hash and the key live on, right? So if you take, for example, Elasticsearch, how many of you use Elasticsearch? So Elasticsearch has got stripes. It doesn't store data on only one location. Whenever you create an Elasticsearch cluster, it sort of stripes data across. So one of the ways in which most of the databases validate that data across whenever they are stored in particular in multiple locations is that it uses a key value to say and hashes the whole thing to say that okay, the hash of this matches against the hash of the other copy. So it matches it doesn't go through each and every, for example, let's say I have 10 records which is striped across 3 systems, right? Now if I lose a network connection, or if it has to make sure that all these 3 copies are exactly the same, it doesn't go through each piece of this copy and compare. Rather it does a hash of the whole thing, hash of the whole thing, hash of the whole thing, and just compares the hash, which is a much more faster operation rather than going through each and every record and comparing and making sure that there is integrity across. So a hash operation is much more faster. So it does 3 operations rather than doing, let's say we have 10 records, 10 into 3 is 30 operations to compare. In fact, it's much more because that's to compare across 3, right? Whereas in the case of a hash compare, it's just 3 operations and one single compare operation across, right? That's the other part. And hashing is also used in cryptography. If you know how public-private key pair works, and so if you use the PKI infrastructure, which is how you move keys across in a public-private key stuff, there the generation of the keys is much more complex. So what we generally do is we store the hashes of the keys, and that's what we transfer across rather than the whole keys. Especially when you want to do validation scenarios, we don't transfer whole keys, rather we only transfer a hash of the key. So that I don't want to go too much into that because it's something that we will do at a much later point in time because cryptography also comes in. And the last part, the most common usage is for password verification, right? Pretty simple. We store a hash of the password, and that's how we move forward on verifying users. I was recently logging onto a site, and they had a password restriction on number of characters you can enter into a password field. That for me says that they're not hashing the password, they're storing it as a plain text, or maybe they're. Whenever you put any restrictions on, hey, your password can't be more than 10 characters, 12 characters, and all that stuff, then there is something majorly wrong with the way they're storing the password, right? But there was a question on this during the last conversation saying, we would like to see around how we use hash functions to store passwords. So that's something that we will get through with the doctors. Anything until now? Any questions? Any observations? I mean, last time I told this is not going to be a one-way conversation. Last time it was much more.
You said that when there are restrictions on password, they are not hashing it. So they might be encrypted in some way or just saving it as plain text. They're using some other.
See, I mean, why would you restrict a user from? Why would you specify a length for a password?
Apart from length, like special characters and caps.
Yeah, why would you specify? You can just if a user wants to enter special characters, anything, right? I can. Why would you restrict them?
Just to make the password a bit complex, so that other users.
But why would you restrict somebody to say your password should only be 10 characters in length, 12 characters in length? Why would you do that?
One reason might be that the table length, column length is 10th, so that's why you can think that it's plain text.
But in the current day and age, do you think that matters?
If you're storing it as plain text, that's the only way, right? That's the only reason you want to restrict it.
Yeah. For me, when I look at that sort of a design, it's because somebody has designed a table in which they put like a varchar 10 or varchar 12 or something like that. And that causes an issue.
They're not hashing it.
Yeah, they're not hashing it. They don't have an idea of, okay, what's the fixed key length that it ultimately. See, if you hash a number, if you hash anything, you know what, it's 128 bits or 256 bits, you know exactly what is the length. However long, if the user gives me a 100 character password, it's still fine. Ultimately, I come up with one key length which is 128 bits. The other thing about a hash function that I forgot to mention, is that the final value of a length of a hash is always fixed, depending on the hash function. There are some hash functions which produce a 128 bit, 126, some 256, some 512. So the final, whatever the value, you take a 10 GB file, push it through a hash function, it ultimately will give a 512 number at the end of it, or a 256 number, right? So that's what it is ultimately. It's always a fixed character in length. There is no variation in the size of the hash function, the output of the hash function, right? And if somebody is restricting, saying it's purely the database schema which is causing that issue, right? Because I tried to enter a 13-character password, it said no, password like this, 12 characters, so reduce it.
It can be a requirement for their own encryption logic.
Yeah, again, I mean, there is password encryption, but even encryption, right,
That
also
is-
produces fixed key links.
That is also level down.
Yeah.
Hashing.
Yeah. Even encryption produces fixed key links, end of the day. Even if you use any encryption algorithm, you can again hash it and again you can get a fixed key link. Right? So that for me is a dicey design when somebody puts that. Right? Any other observations?
The initial character of hash also signifies, right?
Sorry?
Initial character of hash. Now,
Yeah, there's something called a nonce. I don't want to get into nonce because it becomes much more. I mean, last time that's what we went into. It went into different directions. This is good for discussion, but we can go through nonce. I mean, we can talk about sorting nonce, peppers that we use for a password, sorting, and we can go through. So rather than going through a nonce, I will talk about how we can do a sorting, which is more or less similar to a nonce. Nonce, how many of you know what nonce stands for?
I have a question. So nonce means like is that the initial value you pad before the hash 32-bit?
Yeah, so a nonce, it is generally added at the beginning or at the end of a hash. A nonce stands for a number used only once, right? It's a random number which is generated and added to a particular input that you have, which increases the randomness, right? I mean, the thing with the hash function is that it should be as random as possible, right? If there are patterns, let's take. Let's assume you have a million inputs, right? And you hash it and you get a million hash values out of it, right? If there are patterns, for example, let's assume the million inputs that you have, you are substituting one character after the other. Let's say the first one is A, B, C, D, E, F, G. Next you do H, I, J, K, L, M. So you know there is a pattern in this input, right? And you hash it, and if the output also has a pattern, I mean, you can write a program which figures out, hey, I mean, there is a pattern going through this thing, and that helps you to break it. Whereas something like, and that's where the randomness aspect comes in. A hash is supposed to be extremely random. There is no way you should be able to generate a pattern out of a hash. And I don't know if many of you know this, but SHA-1 was broken by Google in 2015, I guess. And
Shattered.
yeah, they broke it basically, and they used one of these functions to figure out that you can generate a collision based on certain patterns that you pass in. Right? So the other aspect of a hash function, it has to be completely random. There is no way that you can generate a pattern out of a hash function. And the current hash function that you have, the SHA-256 and 512, PKFTP2, and a bunch of these things guarantee randomness. And there is one research paper which says there is no way it can be broken down, even if you have like a quantum computer running a bunch of operations for a million years. Some of these algorithms can't be broken down. Right? And that's where we're coming down to. So the properties of a hash function, as we were talking, it has to have a fixed length output. The output length cannot vary. Any arbitrary input that you send in, the output has to be, even if you send a 1 KB file or a 10 GB file or anything that you send in, it has to be a fixed output. The other one, there are two parts, pre-image resistance and second pre-image resistance. So pre-image resistance, that's the technical term that they use. But in simple ways, it just means that it's hard to reverse it back. That is pre-image resistance, right? And that's what we talked about initially. I mean, given a hash value, you cannot figure out what's the input, right? Second pre-image is collisions that we're talking about. It is very hard to have two inputs which result in the same output. There are some hash functions which have been broken because the second pre-image resistance. I have So hash functions are generally living, breathing things. There are a bunch of people who are building hash functions, and a bunch of folks are always trying to break them. For example, NIST, which is the US department which is responsible for security for all US computers used by the Department of Defense and the others. They have a team of folks who are always trying to break all these hash functions, and they also have teams which create these hash functions. I got this from one of the sites that they had, and let me see if I can do justice to this. So this basically talks about the various hash functions and how long they're being successfully used, right? So, for example, SHA-0 has been green up to, I think, 96, 2000. Okay, I'm unable to. So this basically shows like there are certain hash functions, and this is their lifetime basically. And whatever is read, the function has been broken. For example, Git was using SHA-1 some time back, and once it was broken, they had to change Git from using SHA-1 to go to SHA-512 right now, I guess, or RipPMD. I'm not sure. I think it's using RipPMD right now. So right now, Git does double hashing. They don't even do single hashing. Use SHA-512 and the RipPMD to hash your files, right? So basically, as you can see, there are certain hash functions which are no longer used. So whatever was read are no longer secure. They've been successfully broken multiple times. Whatever is hello is suspect. I mean, last year also there were a bunch of Chinese folks who broke some of the hash functions that they had. So it's always an evolving aspect of it, right? So today you might be using a hash function which you think it's secure, it's complete, it's comfortable to use, but you always need to watch out that it could be broken by a collision. And in real life scenarios, right, so most of us feel as developers that hey, this is not important for me. But I've personally been involved in a hack wherein folks tried to use a large e-commerce store's database to get out the passwords. They ran a rainbow table attack basically to sort of say, can we get out email IDs and passwords for a bunch of folks because their cards are saved on the e-commerce store. There were multiple attacks until folks had to get in and sort of put up a firewall to block specific IP addresses and stuff. So as software developers, it's imperative for us to understand how we do it and what is the hash name, how do we store our passwords, how does the hash affect our life, what does it mean on a day-to-day basis, right? I'm sorry I'm unable to expand this properly. Okay, we'll just move forward. Okay, the other two aspects of a hash which are primarily used in hash tables are uniform distribution and random distribution, right? Again, now the uniform aspect of a hash table, of a hashing function is key primarily in a hash table, right? So given a space, a key space, you have to ensure that the hash function generates randomness within that key space. It can't be random outside that key space, and that's what helps in a hash table, right? Again, I'm not trying to get into the mathematics and those aspects. I'm trying to pull it back. And random distribution. Again, it should be random, but again within that key space. It has to be both unique and random. There can't be any pattern as to how it distributes values within that particular key space. At the same time, it has to be uniform. It can't be like it all. So let's say you have a hash table, and all the keys are being generated to the north of the hash table. So you have all the keys bunching up on one side. Then a hash table search does not perform well, right? So these two properties are also pretty unique, but they are primarily used from a search perspective and not from the other aspects of it.
Does it mean actually once the hash is broken, the life is over?
Yeah, exactly. So what generally happens is, for example, SHA-1 was broken and the we broke SHA-1, right? Broken, and that's generally published outside. Let's assume once that's broken and it's outside, there are a lot of websites which have automatic tools built based on that, which you can run and which you can further use it. So, for example, SHA-1 is broken and the method was published by NIST itself, and there are people who have written software which uses that method as built as tools. So, if let's assume you're using SHA-1 as a hashing function in your database, you can run that tool against it and crack your database. Yeah, it takes time, it takes some effort and all that stuff, but still if you want to, you can break it. There is nobody stopping it from happening, right? Any other thing that you guys want to share? I don't like this seating, the last one was better, we were sitting around.
This is more of a classroom.
Okay, some of the functions that you guys primarily know, SHA-1, SHA-256, and those are the key links that we have. You guys want to add any particular hash functions that you guys use? Anything specific that you guys use? Glowfish. Okay, again, there is, since we're talking about Glowfish, on a daily basis, most of us as developers use hash functions for passwords, and that's the primary scenario that we use hash functions, right? Unless and until you are writing your own database, key value stores, then you would use it for different reasons. So when you're using a hash function for a password, so one of the key aspects of SHA-1, SHA-256, they're all very, very fast, right? And that's the key criteria for writing a hash function. But there is another key criteria for writing a hash function for password. That is, it has to be very slow. If you have a very fast hash function for password storage, then it will be broken easily.
Timing attack. Timing attack.
Not necessarily a brute force attack. If you can generate 1 million hashes randomly by brute force, right, every second, and it's damn fast, then there are people who can easily break it just by using raw computing power. So there are hash functions which are very slow. For example, PKFDB2 is a very slow hash function that's primarily used for passwords, and it's deliberately slow. It's very hard to build something that is deliberately slow, right? So that hash function is performing at a particular speed to make sure that no brute force attack can happen using PKDBF2, right? That's one way of slowing down an attacker. The other way of slowing, again, it doesn't guarantee that the attacker won't get through to you, but it's primarily saying that I'll slow it down as much as possible. The other way is multiple hashes. I will show you a program wherein, for example, one of the password storage programs that we wrote hashed a key 5,000 times and then stored the final output. So if an attacker had to attack a site, let's assume we got through the first hash, he had to run through 5,000 such iterations to finally get to the last one. And that slows him down. So if you're using PKFDB2 and multiplying it by 5,000 times, it becomes very, very hard. But still, there are folks who will still attempt to do it. There are folks who will still try to get through to it. So and the other thing that I have seen people do is to use double hash. So first is they make PKDBF2, which is slow. They increase the number of hashes that they have, and they also use a different hash function at the end of it. They will use something like MMD or Glowfish or anything at the end of it, and then they will change it. We'll also look at other aspects like using a nonce, as you were saying, or using a salt. How many of you know about salt and peppers as part of the password? Okay, so we'll get to that. Yeah, so since we're talking about hash attacks, right? So the first one is what we're talking about, the reason why some hash functions are deliberately made slow. So the first one is a collision attack, which is purely a brute force attack. Let's assume one of the general passwords is password 123, right? Most of us would just create like test database or something, use it as a password because it's easy to remember. So that has a hash which has been generated. So that generates a hash, and you have you have tables which has password 123's hash in all the different hash functions, right? So somebody can take that and run it against and compare it against the value that you store in your table. They know this is password 123, and that they can pass it through, right? So similarly, there are websites out there wherein you can get 5 million to 6 million records of passwords stored as hashes. And all you need to do is to run through an iteration, through a for loop, and say, okay, I need to take this and run it through and figure out what the hash that it generates at the end of it, right? So that is a pure brute force attack. And brute force attacks are easy. You have ready-made rainbow tables. In fact, there is a website where you can go and download rainbow tables for Windows XP. Windows XP had a very bad experience because people figured out what was the hashing algorithm that they were using to store passwords. And there was a tool out there which went ahead and generated a rainbow table. It's called a rainbow table because it has all the password hashes of all the common passwords in various hash functions. And it's a for loop which runs through and figures out how to get it out, right? So that's a collision attack that we have. Birthday paradox attack is a variation of the collision attack. It deals a lot with mathematics and probability. There is a theory in probability which is 2 more people in a group of 23. The probability that 2 or more people in a group of 23 people in a particular place share their birthdays more than half That's a pretty good probability number. So what it does is it uses a mathematical function to say what is the probability that this particular hash function is stored in a particular database. And it runs through a probability factor, and it cuts down the collision time by half. So if you have a hash and you are running through it in a for loop, right? Let's assume it takes an hour, but if you use a birthday paradox attack, which is again another tool which is out in the open, and all these tools are freely available. You don't even have to pay for it or spend time. You just go Google for these tools. In fact, I'll give you a link to the website. It takes out this. You can go and download all this and try it. Right? And even tables with. I know of a site where there is a rainbow table with almost 23 to 28 million hash values stored, which are common passwords used across. Recently, when Yahoo was attacked, they took out all the hashes and it's all there available. You can go download, and most of these are common passwords used across. And most of these 23 million passwords that they have a probability of more than 60%. Right? So that's a pretty good number, and that's the reason why now password complexity is being increased, because a lot of passwords that are commonly used are being hashed and stored. Right? And that last one is, yeah, so I'll put the link over here. I'll send this link across so you can. This place is OPH Crack 2. That has a rainbow table with 23 million records. You can go grab it, run it against. If you have a copy of Windows XP, right now it's patched. If you have an unpatched copy of Windows XP, you can run it and break passwords out of it. Right? Anything anybody would want to share? It is not a classroom session. Has any of you been involved in a hack attack, or anybody seen attack unfold across the network? People trying to get into your database, running network scans to figure out which ports are open. Okay, then I hope you don't get through it, but that's a good learning exercise if you have been through something like that. Okay, so I used to work in Dell, so we used to have an attack at least once every 6 to 7 months on our networks. Even though it's a hardened firewall, there are people smart enough to still figure out which ports are open, how can you get in. There are people who would run, especially rainbow table attacks are pretty common 4 years back, when it became sort of the norm, and there were a bunch of kids who would get access to these rainbow tables. It was not that common that you could go download it, but it's still available on a bunch of sites. You had a bunch of tools. You could run it against specific e-commerce websites like eBay, Dell, a bunch of, at that time, Amazon wasn't that much on the radar, but I remember eBay and Dell and a bunch of other companies got hit. People were trying to figure out ways to see which ports are open, are there any database ports open, and they used to come in and run those things on it. Yeah, and this was the SHA-1, how Google went ahead and broke it, and there was unconfirmed reports it was broken earlier by other folks, but it was finally confirmed by Google that they could predictably go ahead and break it at any point in time, and they published this report out. And as I said, that resulted in a bunch of systems which are impacted. Git was primarily impacted. Even Google Drive or some other online system which was backing files also had SHA-1, and they couldn't verify integrity of some of those files based on this, so they had to go back and change their hash algorithms. And this is basically how long it would have taken for somebody even. And the other thing is, Google used commodity hardware. They didn't use like specialized hardware. They went ahead and procured a bunch of AWS, Amazon Web Services. It cost them pretty less also. It wasn't like a huge $1 million sum that they had to pay to go ahead and get it done. It was like 45K or something that they had to pay to go get a bunch of VMs and go ahead and crack it. It was not very expensive. Somebody like that, right? Anything else? This time is much more quieter. Last time. Okay, so we'll come back to the main reason why we are here. So how is hashing used in blockchain? Last time we talked about it, right? There are a lot of hashes in blockchain. Hashing is used almost everywhere. Okay, should we get into blockchain, or do you guys want to see the I had a small piece of code that I wrote this, do the user ID, password stuff. Do you guys want to see that, or do you guys want to get into this? code. Okay. Okay, how many of you are comfortable with C Sharp? One. Okay. You're all object-oriented programmers, you can understand class, object, all that stuff, right? Okay, cool. So I try to make it as simple as possible. I have this as the user class. It's basically got user ID I've used as a name and the password, and there is something called as a sort. So how many of you know what a salt and a pepper is, or a nonce? Nonce, we said it's a unique. So a salt is nothing but a nonce on a password, right? We're increasing the randomness of the password. So most of us as human beings use passwords which are common, right? The probability of a password being reused by many of us in this room is very, very high. So we need to randomize it a bit so that people can't guess it easily. And that's the reason why we add something which is random to a password to make it, and we remove the dependency on the end user to have to remember that randomness, right? So what generally happens is that most of the systems generate a random key which is called as a salt. And the beauty of a salt is the salt is not hidden anywhere. It's stored within the same database. So the same database you store your user ID, password, the salt is stored there. So a salt is nothing but a random number, and generating random numbers is hard, right? How many of you know about cryptographic random numbers? CNRG functions. Okay, so there are random number generators which generate random numbers, but in reality they are not random. They're not random enough. There is a pattern because that function also has a pattern. For example, I know one random number generator which depended on the time. It was using time, and based on the time it was generating a random number. So people are able to figure out that doing it based on time, and they were able to work backwards and sort of crack it, saying, okay, this is how it was generating the random number. It's based on the time because that's a pattern that was being used, right? Whereas there are certain other random number generators which are cryptographic random number generators, and they generate purely random numbers, right? For example, a GUID is a common thing that we use across, right? A GUID is supposed to be unique and random at any point in time, but a GUID is also based on the MAC address of the network card that you have in your system. One of the inputs for generating a GUID, you all know what a GUID is, right? So a GUID is like a unique number within the Microsoft ecosystem, right? That depends, one of the inputs for a GUID is the MAC address of your network card, right? That's also something that people figured out, but still it's not been broken in some ways. So let's assume that this is a user object, we have the user's name, and we are storing his password using this. And the thing to note here is we are not storing his password in plain text. His actual password is never stored. What we store is only a hash of the password, right? So that is a user. So this is where the meat of the whole thing is. So let's assume you have a function which okay, so basically I'm creating a new user in this location. The user is registering with his username and password over here. It's very simple. There is nothing else. Just a username and just a password, right? And I'm taking it as arguments for this particular program, right? And once the user is registered, I'm saying, yeah, the user is registered. And what I'm doing after that is that I'm validating the user. Then I'm going and asking the user to enter his username and password again. And I'm validating against the username and password which has been stored earlier, right? Pretty simple. Clear or fine, right? So all this I'm doing in the user manager class. So here, if you really look at it, yeah. So this is where I'm generating, registering the user. So I have this function which takes the username and the password. The first thing that I do is generate the salt. So I'm using a random number generator as I said to generate the salt, right? I'm getting the salt out of it. And once I get the salt, I'm then hashing the salt over here. I just get this function.
So what I'm passing to this function is both the password and the salt, right? And this function takes the password and the salt, and what I'm using is, this is a hashing function, RFC2898. This is again used for passwords because it's a slow hash function. It takes time to hash using this function. So I'm passing the salt, I'm passing the password, and the last one that I'm passing is the iteration count. It's not a single hash, I'm not hashing it just once. So I can even specify how many times I'm hashing it. So I'm hashing this password 2000 times, right, at the end of it. I mean, then you can see that it's really fast to even hash it 2000 times. Even though I'm saying this is a slow hash function, in reality it's not slow at all. Okay? And post that I'm getting a hash password out, and I'm saving a hash password, and I'm saving all of this in an array. Simple as that, right? So I'll just run this. And what I've done is, before I run it, I'll just show you the. Let's change, it shouldn't take this long. It's building. There's something that I've already generally observed. Whenever there is something on the projector, code especially, it always takes time. Yeah, okay. So, yeah. So before I do that, yeah, I'll just show you. So, okay, so so what I've done is on the command line I pass two arguments. I pass my name and password as password into this function, right? And then I should have gone into this. Okay, and as I said, I'm generating the salt here. This is salt that it generated. And again, one other thing is, all these functions deal only with bytes. There is no string. There is so you should be comfortable dealing with bytes. So you should know functions which convert between numbers and bytes. Right? Okay, so I got this salt. Then here I'm generating the password hash. So as I said, that's it. It hashed it 2000 times. This bit, right? And then I get the hash password out. So this is the hash password that I have, and that's what I'm storing in the array, right? So this is a array. There is a registered user array. So I'm storing the name, the salt, and the. So assume that this is a table. So basically, you have a table in which you're storing the user ID. You're storing the salt for that particular user. And you're also storing his hash password. The password is not being stored in clear text, the password is not being encrypted. There's no cryptography involved in this because cryptography always carries the risk of it being broken. It's pure hash, nothing else, right? So I'm adding the user to the array. Wow. And as usual, things crash when you put it on the projector. Yeah, that's it. Okay, so this is what it is. So I have a user register with a salt of this, and this is the ultimate hash password that we got. Right? Now, if I need to validate the user, let's assume I enter the right user ID and password, which is again password. It validates and it's successfully logging in, right? So I just write again the environment. So here we're not storing the user password, we're not storing it in any way at all. And even if somebody manages to get onto our database, there is no way you can get the user's credentials at all by any chance, right? He'll only get a hash that's been hashed 2000 times. He doesn't know what is the hash function that we're using. He doesn't know what is the salt that we're using. Sorry, he knows the salt that we're using. The salt is out there in the open. But even with the salt, he'll not be able to do anything with it, right? Some systems take it a bit further. They have a concept of so this salt is out in the open, right? Some systems take it a bit further. They generate a salt which is not stored in the open. The salt is stored in a user secrets key value, or it's not stored in the database, right? So I've seen one implementation wherein the salt was a standard hash that they had, which is stored in a registry, and that's what they would use every time to, and that's called pepper. Basically, it's not out there in the open. So there is the user's password which is hashed, there is a salt which is out in the open, and then there is a pepper added at the end of it, which is not out in the open, right? So even if anybody figures out the cryptographic function being used, even if they're able to break it, let's assume you're using SHA-1 and they're able to break it, they still don't know what's the pepper that you have, unless and until they're able to get into your key vault to figure out what is the pepper that you have used to randomly add some numbers at the end of it, right? So this is a very simple example of using hashing, and this is generally how this is generally the right way of doing user credentials, right? Again, I wouldn't say this is exactly production quality stuff, and this is how it is generally done. But this gives you an idea of how we use hashing to store user passwords and user credentials. In fact, even other parts of your user credential, like email ID and a bunch of things, you generally store it using hashes. Like for example, if you do Facebook and all these guys right now, nobody uses user ID. They all use your email as your user ID, right? So all that is hashed and stored. Nobody stores it, even in cryptographic terms, right? So any questions, any observations, anything?
But I see that you said you're storing three things: hashed password, username, and salt. Yeah, so now I have made a couple of applications, and I've always stored a hash password using Bcrypt, using Blowfish.
Yeah, Bcrypt, yeah, perfect, yeah.
And similarly, we generate salt like you do, but we never store the salt. So I'm
Curious as to what.
Yeah,
Yeah, perfect. So even if you store this, let's assume I don't know the salt, or let's assume I know the salt right now. It's stored out in the open, right? Somebody gets into the. Even if he knows the salt, it's still very hard because he doesn't know what's the hash function that I've used. He doesn't know how many times I've hashed. The salt is there, but he doesn't know where is the salt being added.
But for verifying, like you said, salt is added to the password. Like your password is a password, and your salt is, let's say, 123.
Yeah.
Your actual password is password 123, which is hashed, right?
Yeah.
So when I'm going to verify, I have to know the salt.
Add the salt. Yeah. You
But
have to
if
know
the salt is not stored, where is that?
No, the salt is stored, right?
But I said in Bcrypt, we don't store the salt in DB.
So Bcrypt doesn't have a salting functionality. Bcrypt only hashes directly. Bcrypt has a salt?
That's what they have generate salt, and
I don't.
because I gave a salt round,
I don't remember because I haven't used Bcrypt. I know Bcrypt does something similar.
unless they store the salt with the hash somehow.
But Bcrypt has to know the salt because the salt has to be added to whatever the user enters. The salt has to be added, and then you have to run through the hash to finally get the hash value. Without knowing the salt, there is no way you can again get back.
Somehow it knows.
So the salt. So either the salt is stored, or Bcrypt knows there is a standard function to even generate the salt. So there are many ways of generating the salt. So the salt right now that I've generated is purely a random number salt, right? Some people even use a hash of a particular value as a salt. So for example, the user's name can be hashed, and that can be used as a salt.
That way, because we give
get that, right?
we give the salt round. So it knows that it has to salt maybe 10. It's number 10 or 9 or 8. So it knows that, and it knows username or some standard value. So it knows how to create a salt and then add to the password. And
Yeah. See, I mean, here the salt is a random number generator, but the salt can also be a hash value generator, right? And you can generate a salt using a hash value similar to this. You can use another hash function to generate a salt, and you can pass an input, something that is again unique to that particular user. It could even be, for example,
one of the sorting mechanisms that I know of is the date and time in which the user account was created. The user is an input to a random number generator, and that generates like a particular sort based on the time and date that the user account was created. Right? So bgrep does sorting, but I'm not sure where it stores the salt and how it stores the salt. I'm not sure about that. Maybe that's something that you can check in next time. But bgrep is generally that particular library is used in a lot of places to generate hash passwords and salts. How many of you here use bgrep? Do you know about it?
So I was just reading about it. So somehow stored within the hash. It's dependent to the hash.
Or maybe it's a nonce that is the beginning 4 or
$2
beginning 8.
is always there.
Yeah. The
It's
beginning.
generated. The 2A is the version number. Then there's a cost factor. Then this says that it encrypts some known string using those parameters. And there's
Yeah. So what is that known string? That is the input, right? That is the key to the sort. Okay, we'll figure that out. Anything else about this?
Is salt is acted similar as public key in
Not necessarily. A public key, if you really look at public-private key pairs, right? A public key is something that uniquely identifies a person, and that or an addressee at the end of the day, right? That is a much larger connotation than a salt. A salt is just adding randomness, right? For example, some of the most common passwords are actors' names, movies' names, pet dog names are generally common. So there is no randomness in it. People generally use. There was one study which said Julia Roberts was one of the famous passwords that people had during a particular time frame. I don't know, it's like 96 or 97. Pretty Woman got at least. I don't know which year. And that time Julia Roberts was one of the common passwords that people were using, and there was a complete hash of it, and it was getting cracked easily, right? So what a salt does is that it adds. All of us would have Julia Roberts as our password, but the salt will still add randomness to all of us. Right? There's no way you can, even though you know that Julia Roberts is part of the password for all these folks, if you have a salt, there is a randomness assigned to it. So it still becomes a unique password here. Right? It just increases the uniqueness factor. Whereas a public-private keeper is a much larger connotation. Anything else? Which more pointer is there? Okay, so we will talk about this consistent hashing a bit. Sorry?
consistent hashing.
So, consistent hashing is, I don't have any take about it. So, let's assume hash is at the end of the day a piece of code which takes an input and produces an output, right? It could be a simple string, it could be a binary object, and it has to produce a fixed length output at the end of the day, right? Now, the beauty of a hash function is that output that it produces should be unique. Let's assume you pass, it should be unique for unique inputs, right? So let's assume you pass a string which is hashing into a hash function. The output that it produces should be the same every time you pass a string hash into it. It cannot vary, right? But at the same time, if you pass 10 different words into it, the output that it produces should be completely different. Let's assume you pass HASH in capital, you pass HASH in small, the output that it produces should be completely unique. And let's assume you do a capital H ASH, then you do small h, capital ASH, so you're generating patterns out of it, right? But then the output that it produces should not have similar patterns coming out. And I'm talking about like a 4-character word, so the variations are very small. But if you're talking about like a huge database with 1 million records, right? Even then the pattern that it produces should not, there should be no pattern to the output that it produces. If there is a pattern, then there is a collision that's happening. And that's not exactly a collision. In pure terms, a collision is if the output is exactly the same when two inputs are different, right? But for me, even patterns are in some ways indicative of a collision, because once you are able to generate a pattern out of it, right? It's not very far before it can be broken. Because once, imagine if you had to write a hash function. to generate that randomness in the hash function is very hard, and that's the reason why writing a random number. How many of us have tried to write a random number generator? Or can you tell me the logic to create a random number generator? How do you create a random number generator? What logic would you use? There's so many of us here. I mean, how would you generate a random number? Pseudocode to generate a random number. Interview question.
Math.random.
Huh?
I use math.random.
Okay, let's assume you had to build that function math. How would you build it?
So you know, some application which say move your mouse to increase randomness, while I think Bitcoin or something.
So what does moving the mouse, how does it increase randomness?
The coordinates, you know, where the mouse is, it's random, maybe. And I think some of the functions also use CPU temperature or some things like that.
Yeah. So what you're saying is correct. I mean, those are some of the inputs.
Yeah.
And if you really look at it, they're all physical parts of it, right? I mean, that's other to generate randomness. They're using, like you were saying, CPU temperature is being used. The mouse movement is being used. That's trying to generate randomness out of physical random actions. Let's assume, because that's one way of solving the problem. Let's assume there is no physical aspect to it. Time is not random. If you generate a random number using time, so let's assume now it is 11 hours, 30 minutes, 52 seconds. Next second I know it's 53. It's not random. How else do you generate random numbers? Without any physical input. I mean, physical input is one way. It's a very simple problem, right? Generating a random number.
Very fundamental.
And this is an interview question actually. How would you generate a random number? Okay, let's not. There is a lot of maths involved in generating random numbers. Right? There are some people who use a bunch of arrays, ragged arrays, and then they run through the particular array, and then they generate a particular sequence of numbers out of it. But those arrays are big. They have to make sure that those arrays are large numbers. But still, it's not guaranteed to be unique. It's still not a mathematically, cryptographically random number. It's just a random number which you can use at any point in time, but there's no guarantee of collisions.
Pseudo-random.
It's pseudo-random, primarily. Right? Anything else?
It's a chicken and egg problem. It's like I was thinking I'll have an array of numbers and I'll stop at a random number to generate that random number. But
when will you decide? When will you stop? How will you decide?
How will you decide where to stop?
Exactly. So when you move your mouse and all that, as you said, you're using those coordinates. So it's very hard to generate random numbers. Okay. Anything else before we move into blockchain? Okay. From a blockchain perspective, as hashes are there everywhere in blockchain. I mean, if you're dealing with Bitcoin, the Bitcoin block that you refer to as the latest block is a hash of the block. Nobody talks about the whole address, it's rather the hash of the address of the block. If you're talking about transferring Bitcoins or transferring Ether to somebody, you generally transfer it to a particular hash, which is the address of the recipient, right? And if you're talking about transactions within a block, we're only talking again about hashes within that block. Nobody refers to the individual elements within the block. In a blockchain environment, everything is referred to by its hash, which guarantees that everything can be referred to uniquely. In a blockchain, one of the key aspects is that every piece of a blockchain, all the blocks, all the transactions in a block, all the addresses that you have, everything has to be uniquely referred to. And that's where hash functions come in, because hash functions generate unique numbers which can be used to uniquely refer to various elements within a block and also to a block and to the overall blockchain also at any point in time. Right? So some of the places where as we were talking, hashes are used as addresses are derived by hashing keys. And for example, Ethereum uses KSEC256 to generate hash of the addresses, whereas Bitcoin, as I was saying earlier, does both SHA-256 and BMD160. Right? These are hashing algorithms. and these are what is used. You can see the QR code. I mean, if some of you have seen the website, there is a QR code which you can use to transfer. That QR code is nothing but a QR representation of a hash, which is again basically a public key of the end user who is actually at that particular address, right? So the public key is hash. A hash is generated, and that hash is again a QR code is generated out of that hash, which uniquely identifies a particular person, right? Hashes are also used for blocks, transactions, and addresses. I thought I'll just so everything.
Is SHA-256 and the hashback in the same thing?
SHA-256 and
Hashback, hash cache.
Hashcash is different. That's something like Bitcoin. That's another cryptocurrency. Zcash, Hashcash. I mean, that's completely different, right? So this is a block that is there on Bitcoin, and if you can see, all these are hashes, right? And that's the reason why to understand, since we talked about last time, right? What are the key aspects of a blockchain to even understand what a blockchain is, how do we use blockchain, what are various blocks? We have to understand hashing in depth. Without knowing hashing, what hash functions it uses, it doesn't make sense to go forward, right? So a hash is one of the basic fundamental blocks of understanding blockchain. Forget cryptocurrency and all that stuff. To even understand what blockchain is, how do you refer to blocks, how do you refer to individual transactions within a block, how do you refer to addresses within a particular transaction, you need to understand hashes. Even if this is, you can see that everything is a hash. And we'll talk about Merkle roots also. How many of you understand, know Merkle chains?
So Merkle chain is, for example, if this transaction involved, for example, A, B, C. If there are A involves in multiple transactions, the Merkle will be generated for all the transactions and generate a hash of hash of hash.
Hash of hash. So it's a rolling hash. So I have a slide on Merkle trees also, because that's a pretty key concept again in blockchain. I'll not go much in depth about Merkle trees because it's key to understanding blockchain, but it's also sort of, we'll get there. So that similarly, even if you go to the Ethereum blockchain also, it similarly uses hashes. And how many of you saw this? But when Vitalik Buterin was supposed to be dead,
Proof of Vitalik.
and he did a proof of life. He basically showed a hash of the latest block on the Ethereum blockchain to say, "Guys, I'm alive," right? So hashes are everywhere, and there was a pretty famous picture which made sure that Ethereum value doesn't deteriorate rapidly based on false rumors. Okay, so as you were saying, so a hash is a key building concept of a blockchain. As I said, hashes are everywhere, blocks are hashed, transactions are hashed, recipient addresses are hashed. And it's not just hashing individual pieces of data, but a blockchain is a complete hash of a hash of a hash. So I have a representation. So this is what a Merkle tree is, end of the day. I'll just give you a few minutes to look at this so you can process this, and then we'll talk about it. I think you can talk about it rather than me talking about it.
No, I have just gone through.
No man, seriously, it's okay.
Okay. I have minimal understanding on the blockchain. So
Yeah.
what I can understand is, so block one transaction. It contains transaction of multiple transactions. So it hashes of the entire transaction as HA and individually have HB.
Yeah.
And then you pair it two blocks together,
Yeah.
two transactions together, and to generate a hash chain.
Yeah.
And again, the entire blocks, right? The entire chain has one more hash.
Yeah.
Block one, block two, block three.
Yeah.
For example, if somebody
You'll tell you that is not just Oh, good.
yeah. So the reason here is like if somebody wants to intrude any of the blockchain, right, it's difficult for them to understand what this hash contains because he has to decrypt to the multiple hash levels. So it has to go to multiple levels.
So like what I was saying is absolutely perfect, right? So like we discussed last time, one of the fundamental building blocks of a blockchain is that integrity of the blocks. There is no way you can add a false value at any point in time inside a block, right? Because that is key, especially for financial transactions. if you're doing a financial transaction, it's like a ledger that you're maintaining, right? And you have to ensure that each, how does a ledger work? I mean, if you really look at a ledger, there is no way a ledger can go wrong, because even if you make a mistake in a ledger, that mistake is recorded. And then there is a contra entry applied on that top of that mistake to correct it. Nobody like, there is a saying which says accountants don't use erasers, right? The reason they don't use erasers is because they even record their mistakes and then they pass contra entries to correct their mistakes. They don't go back and erase their mistakes, right? So similarly in a blockchain, there is no concept of erasing a mistake. There is no way a mistake can happen on a blockchain, right? And the integrity of a blockchain cannot be questioned at any point in time and to any point back in time also, right? So you can go back to any point in time, check a transaction, that transaction is valid, and as you roll forward, it all gets added up. So if I say I have 100 ethers right now, somebody can go back to my history and verify how I made those 100 ethers, right? Or if I have like 10 10 bitcoins with me, somebody can go back and verify how I got those 10 bitcoins at any point in time, and it's publicly verifiable, right? Because you can go through the various blocks, you can go through the transactions, the various blocks. And the question is, what if somebody, since it's publicly available, like we talked last time, the blockchain is on each of our systems. So when you are on Bitcoin, the whole Bitcoin blockchain is downloaded onto your system. Similarly, if there are 100 people on the Bitcoin blockchain, the whole blockchain is downloaded on all the 100 folks' systems. And any one of us is free to go ahead and muddle around and play around with that particular blockchain. So what stops, let's assume 50 of us get together and decide to change it and change the numbers and all and give all of us another 100 bitcoins for free. What stops people from doing that? Any idea? Anybody thought about that?
The other 50.
The other 50, okay. What if 100 of them also get along and do it?
They have to change it at every place.
Yeah, so
Everyone has.
let's assume somebody has enough to go ahead and change at every place. What happens? As to how many places they can change?
You cannot change it all the places.
Yeah, why?
Because there are a lot of places.
Okay, so we are sort of getting there, right? So the blockchain has millions of blocks, each interconnected. Let's assume I have one block where I made a transaction of 100 bitcoins, right? But I want to some way go ahead and manipulate it to show it was not 100 bitcoins in credit to me, but rather it was 1,000 bitcoins in credit to me, right? So if I want to modify that block, I have to go modify the previous block also, because somebody would have transferred that to me. Now I need to go modify that block. To modify that block, again I need to go back and modify the block previous to that. And there are a million copies of this blockchain on million systems. So I have to modify it a million times across. So that is what a Merkle tree sort of enables us to do. So if you see in a blockchain, if you take each block, generally there are a bunch of transactions within each block, right? So this is like a sample, right? So there is one block which has 4 transactions within it. But generally in Bitcoin and Ethereum, there are much more transactions within each block, right? There are other aspects also within a block. There's a block header and a bunch of other things, but this is for illustrative purposes. So let's assume there are 4 transactions within each block. Now what generally happens is that it builds a binary tree. So A is initially hashed, all these are again hashed, each transaction is hashed, right? So this uniquely identifies this transaction at any point in time, right? Because it's a unique number which is being generated. Each. Just wait for it to come back.
It is always true that it has HASP, always true, or that also is any random number?
Sorry?
Like you're doing 2, right? HASP.
Yeah, so this is a unique, so this is just any hash function. I'm just using this as a mathematical notation to say it's a hash of A.
I think that's fine. I'm saying you're doing 2. Is it always 2 blocks or again like more blocks?
So in a Merkle tree, it's generally, there's a credit and a debit, let's assume, right? What a Merkle tree does is, so it hashes all this and then it takes a hash of 2 blocks. Okay, so it's generally 2, it's a binary tree because it requires 2 leaf nodes, right? It's a binary tree, so it has to balance out. So generally, it is always 2, not just generally, it is always 2 blocks which gets hashed. So each of these blocks are individually hashed, then takes 2 blocks. Let's assume there is a block with, there is also, sorry, go ahead. So there is also another mathematical notation wherein let's assume there is an odd number of blocks, odd number of transactions within a block. What happens in that case? So there is a way of handling that case also. There's an odd number of blocks that do like a contra entry wherein then add an additional block and a hash is generated. So it is a self-balancing binary tree end of the day, right? So the binary tree has to be balanced and then a hash is generated, and finally there is a hash of the whole block as such, right? So what happens is if you want to change any transactions within this, you have to change the hash of the whole, all the other transactions, you have to change the hash through the whole, just to change one, modify one particular block. And not only that, the root of the Merkle tree is a hash of the, includes a hash of the previous block also. And they're all interlinked with each other. So there is no way at any point in time that you can change, even a simple small change in a particular transaction will require you to do like millions of operations. And each of these operations are very expensive operations, right? And again, you have to do it on a million other copies. So there is no way you can break the integrity of a blockchain mathematically. And it's also mathematically proven. There is a concept of a quantum computer. It's like a computer which has unlimited CPU power and all that stuff. So even if you have something like that, it is mathematically improbable to break down a particular blockchain value, right? So that is what a Merkle tree is. I don't want to go too deep because Merkle tree is more about mathematics and binary trees and self-balancing nodes and how we manage it. But this is where again hashing plays a key role. It maintains integrity of each and every block, each and every transaction and the whole node as such. So Merkle trees are a key concept. You can read much more about Merkle trees if you're interested to figure out how it works.
I have a question, sorry. So we talked about
You can always interrupt me.
So I'm just so you said you have a dividend tree transaction occurs. For example, if reversal happens, so in terms of this chain, how would it work?
Let's assume you make a mistake. Okay. So what generally happens is that's either another block where you make the contra entry, or within the same block there is another two transactions happening. Let's assume this was a debit of 10.
Okay.
10 bitcoins was debited here, 10 bitcoins is credited here, then it became a mistake, then you reversed it. And then you said it was 10 bitcoins back credited and debited. So this is where still it's hashed and the integrity is maintained.
So all the system has to be refreshed.
Everybody, yeah, and it is mined. Every transaction is mined. Even if you make a mistake, let's assume, right? We are not going into mining and all that stuff right now. But every transaction is mined. So at the end of the mining operation, what you generate is a hash. That is the whole thing.
Time bound.
Yeah, it is time bound and all that stuff. A mining operation is also generating a hash. End of the day, right? And that's the reason. Even if you make a mistake, it will still get recorded. Same thing as a ledger, and it gets mined and a hash is generated, and that gets balanced out over here within the same block, or maybe in another block much further up, right? So this is what any other questions? And this is what I almost had. I mean, I don't.
So once the Merkle tree is generated, if I want to, let's say, go to the point A where actually the transaction happens, is possible. So now actually the Merkle tree is generated. Now we have a hash value. I want to actually see if some
You
past
cannot
one.
go back with a new man. So let's assume you have one value for this whole block, right?
Yeah.
You can go and see each of these individual transactions.
Okay.
That is always there. I mean, if you go to Etherscan or if you go to the Bitcoin addresses that you have, you can go and see each of these individual transactions. But at the same time, you can also see these hash values against them. That's what I showed previously, right? And you can also see the hash of this whole block. So it's these hashes are generated to maintain integrity, but they don't represent they represent the transactions, but they are not the transactions, right? They are basically being used to maintain integrity of the whole thing. It's like a digital signature for that particular block and that particular
You cannot
transaction.
rectify.
Sorry?
You cannot rectify.
You cannot rectify it. And that's the reason it's a one-way function. Once you have generated this hash for this particular transaction, there is no way you can go and generate another hash. Even if you go and apply the hash function again, it will give you the same output. The output will never change. Nobody can come in and say, if somebody comes and says it was not 10 bitcoins, rather it was 100 bitcoins here, the hash value that's generated out of this function will be completely different. And that's where you validate that the hash value has to be the same at any point in time.
Is that also the reason the value of Bitcoin is always increasing most of the time because it's
No, this has got nothing to do at all with that. It's pure some sort of economics. I don't know what that is.
because obviously it's very expensive. So to do that,
See, it's also because the amount of time and money that's being spent in mining right now. Initially, when Bitcoin was very, very small, I mean, we had a graph last time which showed the size of the blockchain. Initially, like it was 1 MB sometime, and at that time you could mine a Bitcoin in less than a minute, right? But right now it takes hours to mine a Bitcoin on the Bitcoin network, right? So the amount of money it's basically money end of the day that you're spending on mining has to be compensated some way, right? So which means that the value of the Bitcoin has to increase. So that's the reason this is called proof of work. Proof of work is ultimately end of the day you're spending money to mine and generate this hash, right? That's the whole thing. I mean, you're spending a lot of computing power to generate a hash when you mine. That is proof of work that you're doing, right? So people want to move from there to something called proof of stake, which is a different consensus algorithm. We talked about consensus last time. It's a bit disjoint because last time we talked about a bunch of stuff and so while you mine, you're generating a hash, but one of the reasons the value is increasing is the amount of time it's taking to mine. And even add back to the blockchain. Right now it takes like a couple of hours on the Bitcoin network to make sure that your blockchain is up to date with the latest block.
So if you look at the macro level, what if the transaction increases? Like the Bitcoin transaction increases, so will the mining
Time will correspondingly increase as the number. So that's the reason they have this hard split. Even right now it's split. So whenever there are splits, they want to make sure that the amount of time that's being taken to generate the hash value is being reduced. That's one reason why it's one of the reasons why it might split. Recently there was a split for a different set of reasons. 8% of the Bitcoin network went on an alternate chain for specific reasons. But as the size of the blockchain increases, the complexity of mining also increases.
If I can understand, like in the future days, time will require more.
Yeah,
more time will require.
That's the reason they want to move from proof of work to proof of stake. Proof of work means you have input work to generate a hash function, right? And as there are more and more people joining that network and more people mining it, and there is more and more, now there are mining rigs, which are pretty powerful rigs with mining GPUs and all that stuff. So what do? They basically use vector mathematics to generate hash functions, to crack these hash. So hashes work much better with vector mathematics. So your GPU, more than your CPU, it's your GPU which does vector mathematics, because it has to draw this vector for drawings and all that stuff, right? So your GPU does better vector mathematics than your CPU. Your CPU is not built for vector mathematics, right? So people build those rigs, which means that there are more and more people mining, the computing power is increasing. So the whole thing is a computing power. So a whole blockchain, another way of looking at it is the computing power available in the blockchain. As the computing power of the blockchain increases, right, the time taken, the complexity of computing also increases, right? If the computing power is very less, let's assume, I'm just giving a stupid example, maybe, okay. Let's assume everybody has 8086 processors on that mining network. Then somebody with a Intel Core 2 Duo would have the strongest, and you can still mine faster. But then everybody starts having Intel Core 2 Duo, then the complexity increases. Then again the complexity increases. It keeps on increasing. Then the time taken to mine also increases. So that is, it's sort of an arms race in some way.
Yeah.
The more powerful you become, the more complex it becomes, the more riskier it becomes. And that's the reason I want to break it down. I mean, right now there's a lot of research going on making it proof of stake. But making that into proof of stake is, I still don't understand how proof of stake works, honestly. But that's where they want to move. Because there are estimates saying the amount of electricity being used to mine stuff, ecologically it doesn't make sense. I mean, talking about blockchain is very, very interesting, but talking about all the basic fundamental nuts and bolts of the blockchain is much more difficult, right? Anything else? Because
So my understanding of this is that in a block, there, as you saw in that blockchain.info URL, there's always a link to Merkle root hash, right?
yeah,
That's what we should see there.
yeah, I'll just go back to that.
But there's never this Merkle tree is never stored, is it?
The Merkle tree is never stored, but you can build a Merkle tree.
It's
at any
generated
point
and
in time.
validated.
Yeah.
You have transactions, you have
Yeah.
the Merkle root.
So the whole blockchain is actually a Merkle tree. If you really look at it, right? In some ways, the whole blockchain is a Merkle tree because all those blocks, the Merkle tree isn't stored separately. The hash values are stored. But if you want to go back and validate, that's how it validates. It builds a complete Merkle tree and it's going along. So this is the Merkle root for this particular block.
That's why there's no link.
Because you can always go back. Let's look at the Ether. I need to get a. So this is what I had. Anything else, you guys? Okay, the other places where, like we were talking last time, even distributed database systems use Merkle trees to validate their copies, like we talked earlier, right? If you use Cassandra or some other NoSQL systems, where data is not stored in one single location, like Oracle or SQL Server store it in one location, right? Whereas most of the NoSQL systems store data in multiple locations and they ensure integrity using something like a Merkle tree. They basically have a complete transaction list which they hash and they store the Merkle root of it, and that's how they ensure coordination across all copies of their data. Yeah, that's what I had. Anything else that you guys want to share?
Do we know how was the first block mined?
The first block was a manual mine. I mean, there's nothing that they had to.
First transaction.
Satoshi Nakamoto, whoever he is,
No,
he just went ahead and created the first. It's called a Genesis block, right? The Genesis block does not need to be mined.
It's hardcore.
So
It's hard-coded.
It had transactions.
It's hard-coded.
Hard-coded transactions.
It's an hard-coded transaction initially. If you see on Bitcoin, the initial Genesis block does not have any transaction. It's hard-coded and it's basically got a link to a New York Times article about Lehman Brothers crashing. And it talks about, hey, I mean, I want to make sure that the economy is not depending on a bunch of banks, because a lot of people lost their money when that bank crashed. So the initial Genesis block for Bitcoin has no transactions on it, and it's hard-coded. And even the hash on it is just a hash of that particular article.
So when basically you transfer in a transaction, you transfer Bitcoin. Someone need to have first Bitcoin to transfer.
Yes.
No. So how this thing works is when you mine a block and you have 4 transactions, there's always one transaction added extra, the fifth one, the last one, that will be giving the miner the Bitcoin from thin air.
Yeah, that's correct. I mean, for the transaction.
So the first transaction had that only that transaction. So the first 50 Bitcoins were treated like that. Second one had that transaction plus that Coinbase transaction.
See, the monetary aspect of a blockchain, there is sometimes you don't need a monetary. If you are running a private blockchain, right, or a permission blockchain, there is no monetary aspect to it. Like we were talking last time, Airbus is a blockchain implementation, which is for its suppliers or its supply chain management system. Airbus is now one of the largest blockchain networks, right? There is no monetary aspect to it. You mine, Airbus and its partners mine and add information. It's like a database. Airbus and its partners mine and add information to it, but nobody gets any money out of it. The monetary aspect of public blockchains is because people are volunteering to be part of that community. And we need to give back something to that community, right? And the way something gets back to the community is by having a monetary reward. What do you do when you mine a blockchain? Basically, what do you do when you mine a block? You're basically saying, hey, this transaction happened, I'm verifying that this happened, and I'm generating a hash, which is a unique value, which uniquely identifies this chain, right? So there is not just one person, there are a bunch of people who mine and agree. There is 51% of the network which mines and agrees that this transaction happened. So the mining is a way of saying that this really happened. 51% of the people on the network agree that this really happened, right? And one person in some lottery system who's the first person who, again, the person is the highest GPU or CPU power is not the person who ultimately ends up being the first miner. You might have the most powerful system on the blockchain network, but it's still a lottery system. You just because you're the most powerful system and you can mine faster than the others doesn't mean you will be the only person getting it most of the times.
But you get a higher percentage than that.
But you have a higher probability, but it's still not guaranteed. And there are mathematics behind it also, because they want to prevent, we talked about it, they want to prevent governments from getting into this, right? What stops Department of Defense or NIST or somebody, they have huge supercomputers, right? Then they can become the biggest miners and they can control it, right? So the mathematics is your system must be much more powerful than 51% of the systems that they have. So that's a quantum computer. If you have 1 million people with very small laptops on the system, still your computing power must be much more than those 51-52% of people. And even then there's a certain amount of probability that still you won't make it. Any?
I have one question on basic blockchain environment. For example, if Bank A and Bank B, they have blockchain network. And there are two banks like so Bank C and Bank D. So they are running in 2 blockchain networks. Is it possible? Is it possible for the Bank C, Bank D to communicate to Bank A, Bank D's blockchain network?
They can communicate off-band, but they're not on the same blockchain network. Still your transactions, each chain will verify it independently. There will not be a single chain. Let's assume you can, it doesn't happen, but let's assume you can transfer from Ethereum to, you can sell Ethereum, get physical money, you can sell Ether gas. Ethereum is a blockchain network and Bitcoin is a blockchain network, right? You can sell Ether, get physical cash, and you can buy Bitcoin.
Yeah.
It's a similar transaction that you're talking about, right? But these two are independent, so your Bitcoin network won't validate that you sold Ether. Neither will Ether validate that you bought Bitcoin. But still, this transaction is possible, but it has to be maintained by third parties.
Third party.
The thing about a blockchain, for example, forget money for a minute, right? If you take like a supply chain management system, and if you have like 100 vendors all on the same blockchain, right? There is no money involved in this. It's just about transactions being added in a public manner. It's completely visible to everybody. There is no consensus algorithms like two-phase commits or other stuff happening on this network. It's all pretty fast, independently verifiable. It's public. Even though it's public, nobody can modify it, nobody can tamper it. Forget the monetary aspects. Think about how many of us can build a database system and throw it out in the open and make sure that its complete integrity is maintained. That's the hardest part. Let's assume you have Oracle, SQL Server, Elasticsearch Server, or whatever, right? How many of us can put a database on the public node and still say, hey, I can validate every transaction within that database? Blockchain ultimately does that. You can put your complete database. So this is nothing but your banking. Let's assume you are building a banking system and you have a database in the banks. I worked in a banking system. They have huge mainframes, AS400 machines, which have all these ledgers that they are maintaining, and they are hugely secure. There is physical security, a lot of other security around it, right? What blockchain has basically done is taken all those AS400 databases and all those things and put it out in the open. That's what it's basically done, right? I mean, think of it as a bank. You are transacting money, end of it. You are transferring money, you are making money, you are holding money, and it's all out in the public. It's not hidden anywhere. It's not encrypted so that only one person can understand. Anybody can go look at it. Anybody can do any transaction in it. That is the whole beauty of a blockchain. To be able to get sensitive information out in public and still guarantee integrity with it. Any other things?
So in a given blockchain network, to nominate a miner, is there any consensus going on, or how does it work?
Anybody can be a miner.
So I publish a transaction because I'm bank A. So there are some transactions happening in my network. I'm just publishing. Thus I can take any other transaction validate.
Yeah, you can be. So you can publish a transaction. You can also mine a transaction, right? You can. There is no restriction as such. Or you could be somebody. But once you're on the network, you have an option to mine. When you, for example, if you do Ethereum, right? You're down when you do the Ethereum client itself is a mining client. When you download it, it has the capability to mine. But it's up to you whether you participate in that mining operation or not. There are people who specifically get into it because they want the monetary aspect of it, and they are only involved in mining because money is being generated out of thin air, and that's the reason why they get onto it. There are some people legitimately use, for example, Venezuela, somebody went through a huge banking crisis, right? Yeah. At that time, people, their currency went up, inflation was 1,000%, Zimbabwe, 1,000% or something like that, right? At that time, Bitcoin was the most stable currency that they were transacting. People were using that to move money in and out, because the value of that currency was much more stable than their Zimbabwean dollars or whatever that was. Because a loaf of bread went from 10 Zimbabwean whatever currency to like 15,000 something overnight. Okay, so that's what I had. Last time we discussed about this and we decided to do hashing. What do we do next? And who is doing it? Can't be me, man. For me, logically, since we talked, logically next thing would be, like you were saying, public key infrastructure, PKI, because that's what is uniquely used to identify folks on the network, post hashing.
You spoke about Airbus. Is anyone actually working for Airbus?
Anybody works for Airbus? Anybody works for any company which uses blockchain?
So I am working for GE. We are just experimenting on satellite industry. So it's very initial stage.
Last time we had a couple of folks who were using blockchain for health. They basically had built system where you can store your health records in the blockchain and you could publicly provide it to somebody. For example, your health records are locked by a hospital, right? You go for a scan in that hospital holds on to your records, right? But if you go to a different hospital, you either take a physical copy, but the first hospital still has it. So they were building a beautiful solution wherein that health record is in a blockchain, and if you go to a different hospital and if they're connected on that blockchain, they could access your health records. That is a pretty good solution.
So the one which we are working on the configuration aspect. So there is a product life cycle. Right? So I am actually part of aircraft engines.
So you're much more.
So that is the where actually you have a aircraft is having basically 25 or more components, and each component has thousands of parts. So from engineering to manufacturing, actually there are division, what we call the chain design. That's a very difficult to actually manage.
And that's exactly the problem statement that Airbus is working on. So they have same thing. It's product lifecycle management. They're building a PLM software with blockchain as the backend. So like you were saying, if they have a particular component and that component undergoes multiple revisions, there's multiple suppliers, and they have a particular aircraft in which that component is being used, they want those suppliers in the blockchain so that at any point in time, if a supplier supplies a component, there is a transaction that says this supplier supplied this component, this version, and it's permanently recorded over there. So they can take any aircraft and they can come back down the chain to say this component within this aircraft or this particular part is supplied by this supplier.
We can use these models in commercial vehicles.
Yeah, I mean, that's the other part we talked about last time, right? Do not always connect blockchain with Bitcoin, Ethereum, and cryptocurrencies, right? Blockchain is much more larger than all these cryptocurrencies and the economics behind it, right? And as I was saying, it's more about being this open distributed database which people can access in a much more open, collaborative manner with no restrictions. You don't have a user ID password to get onto that network and all that stuff. Yeah, there are permission networks where you provide permission for people to get onto those networks. For example, Hyperledger from the Linux Foundation, that's primarily being used as a permission network. Then Ethereum has its Ethereum Enterprise Alliance, which is again a permission blockchain which is being used for enterprise transactions. And these have nothing to do with any monetary aspects at all. There is no cash.
With the help of blockchain, many business models can pop up in the near future.
A lot of banks that I know, for example, I know some product companies working in banks, banking software, they are doing it. Insurance is being, insurance and finance, they are doing it. PLM and supply chain management is going through it. Health.
Do you have any idea how we can correlate with IoT and blockchain?
There are use cases for IoT and blockchain also, but I don't have anything right at the top of my mind, but there are use cases on IoT and blockchain also. I'm not getting anything out of the top, but I've read use cases on that, but not sure.
There is a non-profit group, right, called Hyperledger.
Hyperledger is the Linux Foundation's. So every of these technologies have two pieces. One, for example, Hyperledger belongs to Linux. It's an open source software which anybody can use. But IBM has taken the Hyperledger part of it and built something called Hyperledger Fabric.
Even they have the new product Composer. Hyperledger Composer.
Yeah, so so they have taken Fabric and what they've done is they've integrated into Bluemix, which is IBM's cloud solution, and they've built a bunch of tools around it, Composer and a bunch of things which allows you to not deal. So if you're using Composer, you don't have to worry about hashing, you don't have to worry about all these things. You just say this is my product. It's like a workflow builder.
It's like a ready-made platform where you can actually work. You can
they abstract the complexity of a blockchain behind it.
with the peers and you should be working with.
So
platform.
that's what it is. So there are a bunch of companies working on it. So Hyperledger, if you take it, it's the open source thing which you can download and you can make changes and build something on your own. Or you can use Hyperledger Fabric, which IBM has already customized, added it onto Bluemix. You can take Ethereum as an open source, download it, change it, and all these are open source. This source code is available on GitHub and a lot of other places. You can go take a look at it, right? So it's about how, for example, Zcash is an extension of some other open source network that they have taken it. So all these are open. And that increases security. I mean, if you develop in closed source, where source code is not visible, that increases your security risk. since all these are open networks and sources available openly, there are people who have gone in and figured out issues and they've gone ahead and corrected those issues.
Even Microsoft Azure is also playing a vital role.
That is where so Microsoft and a bunch of folks are on something called EAA, Ethereum Enterprise Alliance, EEA, sorry. So that is a permission network for Ethereum. Again, there is no Ether, no gas on those networks. You can, again, that is on Azure. So if you get onto Azure, you have I don't know how many of you have seen Azure. Azure has got something called a resource manager template. So it takes you like a couple of minutes to go ahead and get a Ethereum Enterprise Alliance VM up and running. Right? It's just one couple of clicks and you can get a whole blockchain network up and running at any point. You can do smart contracts and all that stuff. Solidity programming. Visual Studio Code has Solidity programming built in. You can write Solidity contracts in Visual Studio Code and all that stuff. But we're not. That's all. Like, much further before you even understand smart contracts. You need to get the basics correct, right?
Are there any instance of Bitcoin store or not in there?
Sorry?
So I attended one of, so Unocoin is I think one of the trading platforms. So I attended one of the session on that. So some customer, actually one of the customer actually said actually my Bitcoin disappeared from his trading account.
Yeah.
So
there have been instances wherein there are two famous. One is something called a Mt. Gox instance.
Japan.
So people basically did not store their wallets securely. So there are a bunch of hackers who figured out how to get into those wallets and take money out. It's got nothing to do with the blockchain network as such, the integrity of the blockchain network. It's about how you store the money. Again, it's being stored in a wallet, and that wallet is outside of your blockchain network, right? If your wallet is not secure, there's nothing that we can do about it. Because all the money that you get out of mining, you have to store it somewhere, right? So it's being stored in wallets, they're not secure. So something similar happened in Ethereum, wherein a smart contract was written badly and money was lost.
No.
Yeah. So, but Ethereum, the beauty of it was a lot of white hat attackers went ahead and cleaned out the whole network. They figured out a lot of people are also vulnerable, so they actually hacked everybody's account and took all that money and kept it safely, fixed the issue, and then put the money back.
But
there were a bunch of around 15 to 16 guys who held nearly $63.5 million or something at one point in time, because they had to pull all the money into a bunch of other.
So in those cases actually you cannot see actually who has done.
Yeah, but it's not a blockchain issue.
Yeah.
You have to understand the blockchain is
Yeah.
nowhere there. Your wallet is completely different from your blockchain. Of course, the blockchain will say you have that much of money at that, but you're storing it, you're converting it, and stored it in your wallet, right? If you're not keeping your wallet secure, which means somebody can impersonate you on the blockchain, basically. So a wallet is nothing but entry into the blockchain, right? So the wallet is your public address, which represents you on the blockchain, right? If I'm able to get onto your private key, if I can take your private key, I can make a transaction on your behalf. So what somebody did is they went ahead and hacked all the private keys and transferred that money out. And you can't identify, right? One of the beauty of a blockchain is you can be anonymous on the blockchain. There is no way you can identify that this person at this particular address is you, right? So they were able to hack it and get the money out.
Blockchain is nothing, just a normal bank passbook kind of thing. It only contains your data.
Distributed ledger technology.
Yeah, contains only your data, no other money and nothing. The money is already stored in your wallet.
So if your wallet is out in the open and people can put their hand in and take it out, it's fine.
If your private key is exposed, you're gone.
It's similar to somebody knowing your internet banking password. If they know your internet banking password, they are you.
Right.
Sorry?
You need ATM card also.
They can use a reader to read your thing. Okay, so that's what I had based on the last time discussion. What do we do next? The question again. Okay, one of the things that we decided last time is it's not just about one person standing and talking all the time. and we also decide on the topics that we do. So last year we decided. Anybody else wants to step up? Okay, so we'll take it offline. We'll have a discussion and. Thanks for coming in. There's coffee available downstairs. This cafeteria is closed. There's coffee and snacks available downstairs if you guys need. And the other thing that we discussed last time is sort of get to know people across and sort of have a.
Last time I wasn't present, so you guys.
There is a video available. I'll send the link. So we are making sure.
I'll check.
The first time for this.
Because it's very hard to summarize. Last time was 2.5 hours. It's very hard to summarize 2.5 hours. So last time we talked about, or you guys can summarize it.
So next meetup can be about summarize the first one.
Generally we do once every fortnight. So it's just, so since we had one today, it's a second after this Saturday after next Saturday. Right? We're making sure that we are consistently doing it every second Saturday as we are going forward. Right? So if you miss it, you miss it. Make sure. Right. Okay, so we'll take it offline as to what we should. But any thoughts on what we should be talking about next?
Cryptography.
Cryptography. You're saying, yeah, I mean that makes sense because that's the next logical.
With hash.